Okay, so I think we're on, Ulises. Okay, welcome everybody to this fourth edition of the National Colloquium for AI. So I'm very proud to introduce you Sepp Hochreiter, who is, well, he doesn't need introduction. He's a very well-known researcher in the field of artificial intelligence. He is actually from Germany, but he works now in Austria. And he obtains his PhD from the Technical University in Munich several years ago. And he actually he started working on the very well-known LSTM networks at that time when he was doing his diploma thesis and his PhD. Now those LSTMs are used for many applications, especially speech and language processing. Google is using them, Amazon is using them. So many big companies are now using the LSTMs introduced in the 90s by Sepp. So Sepp Hochreiter is now heading the Institute for Machine Learning at Linz, the city of Linz in Austria. Also the LIT AI Lab, and he has a collaboration with the company Audi in the field of autonomous driving. He is also director of the Institute of Advanced Research in Artificial Intelligence. So Sepp has been working for many years in applications and the theory of deep learning. He is now investigating different kinds of algorithms, the connection to reinforcement learning, and he has been applying them for the study of climate change, smart cities, drug design, text and language analysis, and also for autonomous driving. Today he will be talking about something that until recently was not that well connected to deep learning. I mean the Hopfield networks. Hopfield networks were used in the 90s as a kind of associative memory, as a kind of discrete associative memory. And in his abstract, Sepp announces that he's going to talk about a new kind of Hopfield network using continuous input and having very interesting properties that can be leveraged in deep learning networks. So without further ado, I'm glad to give the floor to Sepp, and he will explain us what are these new Hopfield networks. Thank you, Sepp, for being here.
Sure. Thank you for this very kind introduction. Perhaps before I start my slideshow, I have to mention Raul was one of my reviewers for my PhD thesis, and he knew about LSTMs before Google, Facebook, and all others know about it. He was the first one to evaluate this stuff, and he did like it and gave me a good mark. Now I will tell you about Hopfield networks. I'm starting to share my screen, and I hope you see it. I'm going to talk about modern Hopfield networks. I will explain what they are and how I think we should use them. So basic ideas, the basic story is, what you see here is a deep neural network, which would be here. And its counterpart, a deep neural network, where each layer, this blue things are layers, is equipped with an associative memory. For us, it would be then Hopfield networks. I suggest to integrate this old stuff, this Hopfield network, into every layer of a deep learning architecture. That would be the idea. That means deep learning would go beyond convolutional neural networks or recurrent neural networks like the LSTMs. Idea is integrate modern Hopfield networks into layers of deep learning, thereby enhance them, gives them a memory, gives them an associative memory. If we do this, what we get is we can associate two sets. We can do pattern search in sets. We can do pooling operations. We can build memories like for LSTMs or gated recurrent units. We can learn prototypes. We even can implement the transformer attention mechanism. We can do sequence-to-sequence learning. We can process and analyze point sets. We can do multiple instance learning. We can do stuff like k-nearest neighbor, support vector machines, or learning vector quantization. Modern Hopfield networks. Modern Hopfield networks were introduced by Krotoff and Hopfield. Yes, it's the Hopfield here in 2016. It's the same Hopfield from the 80s, from 82 and 84, where he made the Hopfield networks popular. He was yesterday in a talk of mine, and he's, I think, 88 years old, but still in the field of artificial intelligence, and was connected via Zoom to my talk. It's very nice. And Krotoff and Hopfield introduced in a Europe's paper this modern Hopfield networks. They were generalized by Demir in 2017. And these modern Hopfield networks have a tremendous increase of the storage capacity, and they converge extremely fast. Standard Hopfield networks, this old stuff you learn in some lectures, say associative memories, date back to the 60s and 70s, and were popularized by John Hopfield in 1982. It's a continuous version in 1984. Standard Hopfield networks. What they do, this is Hopfield networks introduced or popularized by John Hopfield in 82. You have here n patterns. These are binary patterns, x1 to xn. Each component of these patterns is either -1 or +1. You can also do 0 and 1, doesn't matter. And then you construct a weight matrix storage, where you do just the outer product of these vectors. If you do the outer product of these vectors and sum them up, you get this weight matrix, this storage. And then you have a query pattern, a state pattern. It's also a vector having -1 and 1s, a d-dimensional vector. And now you do an update. Here I show you the update rule. The new state is the old state multiplied by this matrix, which is just the outer products of these stored vectors, minus some offset b, and then you take the sign. If you 0, 1, otherwise you have to take 2 times the sign -1. And this would be the synchronous update rule, where all components of Xi are updated at once. There's the asynchronous update rule, where you do this update, you choose only one component and do this update. Convergence is reached if after an update nothing happens anymore, your new state pattern is equal to your old state pattern. And this update rule minimizes the energy. I now wrote down the energy by EB, B for binary. The energy looks like this. Is this state pattern times this matrix where the stored patterns are contained, plus a linear term. Interestingly, this quadratic term here can be written like that. What is it? It's the state pattern Xi multiplied by the patterns. And that's just a dot product, and you do the square of the dot product and sum it up across all patterns you have stored. And you have the linear term, but it's not of interest. This is of importance later, that we can write the energy like that. These old guys, these Hopfield networks, were proven to converge with the asynchronous update rule. We need the main diagonal larger equals 0. With this HEP learning rule, what I showed you as outer product, it's guaranteed. And the weight matrix have to be symmetric, which is for the HEP update rule also guaranteed. So the original version of John Hopfield was where WII, meaning the main diagonal of the storing matrix W, was 0. The synchronous update rule, where all Xi patterns updated at once. we only need that the weight matrix is symmetric, but we can only prove that it's converging to a stable state, or, and that's the problem, to a limit circle cycle of length 2, meaning it's alternating. It's not sticking at one convergence point, but it's alternating at the end. That's what these standard Hopfield networks are doing. You see an image of Homer from The Simpsons, but half of the image is masked out. Now you throw it into this Hopfield networks, and after energy minimization, you get out the full picture. It's remembering the full picture. You can do this with more pictures stored, but now with the standard Hopfield networks, unwanted things happen. Like in the first row, you see you throw in a part of this image, the other half is masked out, but you get a different image, and it's even inverse, white and black interchanged. Or what you see here in the second row, stored was one pattern, was a dominant, was more often stored, and then you get the dominant pattern back, and not the pattern you want to retrieve, which would be Homer in this case. Here, another typical case, here we stored in the standard binary Hopfield networks, the stuff from 82, many patterns. But the problem with these patterns is they are correlated, they are overlapping. And then if you want to do retrieval, you do half of the Homer, you give in, and what you get is sort of an average of all these patterns we see here. And that's not what you want to have. You wanted to retrieve the image of Homer. You see, standard Hopfield networks have problems if patterns are correlated, if they have many bits in common. And this is reflected by the storage capacity. How many patterns can I store without having these overlaps on average? And that's linear in D. D is the space in which these patterns live. It's the length of these vectors, of these binary vectors. And if you want to retrieve without errors, you have D divided by term in log D. If you allow small retrieval errors, it's 0.14 times D. It's linear in the space where these patterns live. And that's not much you can store. And recently, with the seminal paper of Dima Krotov and John Hopfield, the energy was changed. It's still a binary energy, therefore this B here. But now, if you remember, I showed you this formula where this in brackets was squared. Now, instead of squaring it, we say, hey, let's use a function, capital F, which is called an interaction function. And this function is just a polynomial where it's to the exponent a. If a is equals 0, if a is equals 2, then we have the classical Hopfield network. It's a Hopfield network I showed you before, where this term was the important term, except a linear term. But if we have different a, like a 3, 4, or higher, then we have new properties. I come to these new properties. But first of all, I showed you for the classical Hopfield law how energy minimization worked. It was only multiplying the state pattern Xi with this matrix W. But how should we minimize the energy here? It's quite simple. What you do, you have a state pattern, and now you compute the state pattern where the J's component, the component J, is 1 versus where the J's component, the component number J of Xi is -1. And you compare the energy. You flip one component of the state pattern and look, where do I get lower energy? And if I got lower energy, if I flip the sign of this component, then I choose this component, the component with lower energy. and that's an asynchronous update rule, and this update rule converges, can be shown to converge to an energy minimum. Of this energy here, the energy with this new interaction function. But what we now have, this storage capacity is now polynomial in D. Without errors, we get this property. It's D to the power A minus 1. For A equals 2, we know that's a classical Hopfield network. We get linear storage capacity. We know that. But if we increase A 4, 5, 10, 20, we get high storage capacity. And the same with retrieval error. With small retrieval error, we get some constant. And then again, it's polynomial in D, and the exponent is governed by this A. And this A comes from the energy function. Instead of a quadratic term of the dot products, we now use terms which to the power of A. These modern Hopfield networks were generalized by Dirimitzi-Gil in 2017. And what they just did is there's this interaction function, and Krotov used polynomials. They use the exponential function. As interaction function, the exponential function. What do they get is a storage capacity which is even exponential in the dimension of the patterns, the length of the patterns. Here, 2 to the power of D half. And there's another very nice property. What we have here is more or less saying we converge even after one update, meaning that the update of the pattern I have right now is not the fixed point, is not the stored pattern, goes to zero with increasing dimension. Meaning the probability that you find an update which does not converge goes to zero. Meaning it's very likely that after one update, you already have your stored pattern. And that's the second property. You only need one update to converge, and you have exponential storage capacity. Two cool things. And now if we look what happens with HOMA in this case, we know the first row, the standard binary Hopfield networks, we get this kind of averaging over all the patterns. But when we do the modern binary Hopfield networks, we can retrieve HOMA even if you only know half of the image of HOMA. And this shows, yes, the storage capacity is higher. These networks are more powerful. And even if we store many more patterns which are highly correlated, because also pixels are correlated, it still is working with modern binary Hopfield networks. We can still retrieve HOMA or half. If we only give half of the HOMA, we get the whole HOMA. It's working. And it's working because this new energy function pulls apart these patterns. If patterns are correlated, share the same pixels, the new energy function pulls them apart because of this polynomial, of this higher polynomial. You can distinguish the different patterns. Now I come to our work. This is very intriguing. It's very cool stuff, this modern Hopfield networks. And the idea, as I said, is we want to integrate these modern Hopfield networks in deep learning architectures. So that's a deep learning, deep neural network. And here we want to have these modern Hopfield networks in every layer. In every layer, we want to have an additional associative memory. But we know these modern Hopfield networks are binary. But still, we want to do gradient descent through the network. And here we have a problem with this binary Hopfield network. We cannot guarantee differentiability. It would not work to do backpropagation if we have this binary Hopfield networks. What we need is continuous Hopfield networks. also continuous differentiable Hopfield networks. Then we still can use our backpropagation algorithms, and we can propagate through this associative memory, which would be sort of cool. Also, what we want to have from the binary Hopfield networks, from the modern binary Hopfield network, is retrieval with one update. Because if we can retrieve with one update, it is the same as activating the layer or doing one update. Therefore, we don't have to change our programs, because activation of the layer is the same as doing one update. It's one computation, is one procedure, and not an iterative procedure. Also, this would go very nice with what we already know from deep neural networks. And we also want to keep the high storage capacity to get a lot of patterns stored in this associative memory. And now I want to show you how to construct this. Again, we have n patterns. We have capital N patterns xi, but now they are not binary. They are from r to the power of d. They are real numbers. So we can construct a pattern matrix where each of this pattern is a column, and we get a matrix. We need a constant which gives us the maximal norm of the patterns. It's a Euclidean norm. We still have the query pattern, but now this query pattern is a continuous vector. It's not any longer a binary vector. And what we need is the log sum exponential function. And this function looks like this. It's equipped with a beta. It's more or less the inverse temperature. This is beta to the -1 log. And now the sum over this exponentials, beta times AI. AI is one of the components of this vector A. This is a log sum exponential. Using this function, we have defined a new energy function. The new energy function looks like this. The energy, now there's no B index, because now we have a continuous energy function. This is a pattern matrix transpose times xi. This means xi is multiplied to the first pattern, xi is multiplied to the second pattern, xi is multiplied to the third pattern. We have all these dot products, and then it's the LSE of all these dot products. That's the LSE, where we have a vector, and components of the vectors are also dot products of xi with different patterns. And we have a quadratic term here, xi transpose xi. We need this term because it's a continuous Hopfield networks, and the state pattern is not bounded. And then some constants. The constants are not of interest. And the energy function of de Moivre can be written like this. And we see already a similarity of this energy function of the binary modern Hopfield networks with our new Hopfield networks. Ours works for continuous patterns. This works for binary patterns. And it turns out that with this energy function, we can keep the exponential storage capacity, I will show, and we can keep that after one update, we already retrieved the pattern. And the constant are only there because to bound the energy between 0 and some constant. The energy function also comes with a new update rule. And the update rule looks like that. It's the new xi, the new pattern is x, that's a data matrix, times p, and p is the softmax. The softmax function of all these dot products, between xi and also patterns. This term is always the vector of dot products between the state pattern and the stored patterns. That's our new update rule. And now I will show you some properties of the new update rule. First of all, we can prove that's converging. Converging in this sense means that's Zangwill's converges theorem. Converging means that the energy converges to some energy minimum. But I go to the next slide. Convergence can be even enforced. The first theorem only told us that the energy is converging, that with more and more updates, the energy goes to a minimum. What we want to have also that the state pattern goes to some fixed point, to this fixed point. This theorem is telling us this more or less. The theorem says if we do the iteration, then we end up in a local minima or a saddle point. We never saw saddle points. We end up in local minima. Except, and this is the thing, there's a manifold of connected local minima, and there's an exception. That's only of this, so most of this theorem talks about this connected manifolds of minima. But if you have a single minimum, then the iteration will hit one of these minimal points and be in a local minima of the energy function. Therefore, this update rule really makes sense. We can show it goes to a minimum, except there would be a saddle point, but we never encountered one until now. Now to the storage capacity. A problem is with a binary Hopfield network, we know what retrieving means, but for a continuous form of Hopfield network, we first have to define what we really mean with storing, what we really mean with retrieving. And storing is defined here. We assume that around every pattern X, there's a sphere. We have some sphere around each pattern. And X is stored if in this sphere is one fixed point only, there's one fixed point, and all points in the sphere converge to this fixed point. Also X converges to this fixed point. But this fixed point is not, or is not necessarily, this stored pattern. And what we also need, these spheres, they have no points in common. The intersection is the empty set. So I don't share any points. Therefore, if I'm in one sphere, I converge to this xi, and actually I have retrieved the pattern xi. And when do we say something is retrieved? We don't want to go to the fixed point because it takes a long time. We say xi is retrieved if the iteration is epsilon close to the fixed point. If the point we get from the iteration at some point at the iteration is epsilon close to the fixed point, then we stop the iteration. Then we say, okay, we now have retrieved it. So retrieval error is the difference, the Euclidean difference between this point, where the iteration ends, and the stored pattern, which means this guy goes towards the fixed point, and the fixed point has still a certain difference to the stored pattern. But that's our definition of storing and retrieving. Each stored pattern is identified by the fixed point. We go epsilon close to this fixed point. Now with these definitions, we can talk about the storage capacity. I don't go into this theorem. I only want to tell you the result. The result is, yes, the storage capacity, n is the number of patterns, is exponential in D, exponential in the dimension of the space where this continuous pattern now live. We have a P here because this is storage of randomly chosen patterns. There can go something wrong because by chance you choose patterns you cannot store well. And the C depends also on the length of the patterns. If you have very small patterns, the norm is very small, I cannot store it. And we have other terms depending on the dimension, on the length of the pattern, and so on. And the C can be, for some settings, something like 3.15, or the C is 1.37, depending on which K we choose, which dimension we choose, and so forth and so on. But we get an exponential storage capacity, which is a nice thing. And now retrieval. I said we want to have retrieval with one update. Then we can use our deep learning architectures like we used them before. And retrieval of a pattern for a fixed point and a query means the update of this query is epsilon close to the fixed point. Then the pattern is retrieved. And Then is the question, what is retrieval error? I came next to this, but before going to the retrieval error and how fast it converges, I need another thing. It's separation of a pattern. Delta gives me the separation of a pattern. The separation means how large is the difference of the dot product of a pattern with itself minus the dot product of the same pattern with other patterns. If this is a large number, then this pattern is similar to itself, but not similar to other patterns. That's the separation. Separation in terms of dot product. How far are the patterns different from each other? And if a pattern is well separated from the other pattern, we have a nice property. And the first property is we can have a retrieval with one update, and we can derive this formula that the difference between the update and the fixed point is smaller than this Jacobian. It's a Jacobian times the original difference between the query and the fixed point. But interesting for this Jacobian we see is exponential minus beta, this is the inverse energy, times this delta. And there are other constants, some differences, but this is the main thing. If the pattern is well separated, and we in a high dimensional space, we get a large value of this delta of this separation. And this is the dominant term. Everything else is not so important. This is the dominant part, and this is exponentially small, meaning the difference to the fixed point after one update, if the pattern is well separated, given by this delta, is exponentially small. With one jump, with one update, we are very close to the fixed point. We are very, very close to the fixed point. We don't need another update because we already is there. And this means if the separation is large enough, then we will go epsilon close to the fixed point. And it only depends whether this pattern is not similar to other patterns in terms of dot products. And so the second thing we have is the retrieval error is exponentially small. So retrieval error is now a little bit different from the convergence, from the retrieval. This is the pattern we get after one update minus the stored patterns. How far we are away from the stored pattern. We get the same or very similar formula. We have now here two terms. Again, minus beta times the separation. And then we have something like the maximal distance of the original xi to the pattern, and the difference of the fixed point to the pattern. We know this is also exponentially small. Here an example, if you say this is smaller than 1 over m, this is smaller than 1 over m, there's also beta in here, then we get this formula. We see this is immediately smaller, very small, it's exponentially small, depending on the separation. If we have in the separation, this delta gets larger if we in high dimensional space. If we have many dimensions, then the dot products become larger, and therefore we get large terms here. What happens if all patterns are close to each other? If the dot product of a pattern with itself is almost the same as a dot product of the same pattern with other patterns, since the patterns are not well separated, no pattern is separated, and the iterate converges to a global fixed point. And this fixed point is actually the arithmetic mean of all the stored vectors. In this case, the softmax is a uniform distribution. Softmax is 1 over n. Every pattern is weighted by the softmax by 1 over n, is weighted equally. And here now the most interesting stuff, this is the metastable states. Metastable states we observe if some vectors are similar to each other, and the patterns which are similar to each other, they are separated from all other patterns. So they're similar to each other. There's a small crowd of patterns, a small cluster, but the cluster is separated from all other patterns. Then we get a fixed point in the middle of these similar vectors, amongst the similar vectors, we have this fixed point. So fixed point is sort of an average of the similar patterns. And that is the most observed state new Hopfield network is converging to. Here, the new modern Hopfield network, the continuous Hopfield network in action. Again, a HOMA, but now you see the grayscale, it's real values. And if you store this many patterns, so correlated, we can retrieve the image of HOMA very well. With this kind of beta, but as soon as we reduce beta, meaning we increase the temperature, we only get an average of all these patterns. We now get this pattern, which is actually an average of all the stored pattern. Beta is something like the inverse temperature. With high temperature, we only get an average. With low temperature, we can retrieve the pattern. Here, an example how beta is increased. With a small beta, meaning high temperature, we get averaging. And by increasing beta, meaning it's the same as decreasing the temperature, we more and more see HOMA. It's less averaged over all the patterns. It's only this one pattern, the softmax, has only one high entry, which is the entry for this stored pattern. Here, examples, here two-dimensional space also with beta increased. So here also I show as energy. Low energy is bright, high energy is red. Here we have an energy minimum in the middle. It's this global averaging point. This is the global average over all these dot points, black points. Each black point is a stored pattern, is one of the patterns, and that is a retrieve pattern. For small beta, we get only the arithmetic mean of all these black dots. But if we increase beta, now we get two local minima, which averages over the patterns, the black patterns nearby. And if we still increase patterns, now we get four local minima. Here's a local minimum, here's a local minimum, here's a local minimum, here a local minimum. And we see already now the local minimum sits on top of these black patterns, and this gets more and more precise. Here's green dots, which are the minimas, are sitting exactly on top of this largest black dots. And we also see that the space is divided into four squares. Also this happens. Here I have the same thing once again. Here I want to show you different dynamics, what we have. What we can have here now, it's a blue dots as a stored patterns, and I start with each of the stored patterns. I start an update and look how the stored patterns would evolve towards I would converge. In this case, it's something like I have a very large beta, very low temperature. The stored patterns sit on top of the stored patterns, I don't change. Here is the opposite, very small beta. We only have one global minimum, it's in the middle. But we also get all different other kinds of minima. Here, a high beta, where the blue dots are close to the original points. Only in a local environment, the data points are drawn into the minima. Here we have, for example, four minima with strange patterns. Here we have more minima, meaning we can now produce all kinds of dynamics of this modern Hopfield networks, storing one pattern, averaging over patterns, averaging over a local group, averaging over a larger group, averaging over small groups and large groups, and so forth. It's the same again. Now, I want to change a little bit the topic. these new Hopfield networks, and that's surprising, are the tension mechanisms of the transformer. Perhaps you heard about transformer. Transformer took over NLP. Perhaps you heard about GPT-3. That's a transformer mechanism. And these new language processing systems are very successful in all kinds of language tasks and text tasks. And this is the transformer architecture. And the transformer architecture is based on this transformer attention. And it turns out that our update rule is exactly the transformer attention. I showed it here with formulas. Here it's embedded in a neural network, therefore we have to include weights. But I show you this slide. So first, most left box is the Hopfield network, the modern Hopfield network with binary patterns. Then that's our new energy function. That's our update rule. And now we see our update rule resembles the attention mechanisms of the transformer, of this deep learning architectures, which are now so successful, which are used in language processing. Therefore, we should integrate our update rule somehow into these deep learning architectures. And that's exactly what we want to do. This is the modern Hopfield networks. That's the update rule. The update rule is more or less the softmax of beta times R. R are the query patterns, the patterns which probes associative memory. We have a Y, this is the stored patterns. And on the outside, that's coming from the update rule, we have again the stored patterns. And that's how this is working. We have some stored patterns. Here's the Simpsons. The stored patterns here, it's here. And here we have queries. We can also have more than one query here. That's how the modern Hopfield networks work. And now this update rule, as I already said, is the same update rule as used in transformers and calls the attention. This is attention mechanisms of the transformer. But now with the new idea of using associative memories, we can do much more. We don't only have the transformer attention, but we have much more ideas. I have an overview here. This is more or less the transformer attention mechanism. The transformer attention get queries and get the stored patterns. And both the queries and the stored patterns come from the previous layers or from some previous layer. So attention mechanisms of transformer use this and this. This is the results from a previous layer. That's what transformer are doing. But now we can also build other layers like Hopfield pooling, we call it. Here, some Ys come in from the outside. So Ys here, for example, might be multiple instances for multiple instance learning, or a time series which is stored here. And now we learn, it's not computed, it's learned what are good queries to probe this data which we store here in the associative memories. We learn the queries. There's another layer, the Hopfield layer. Here we say we propagate the queries. We store something here. This stored thing could be the training data, could be also learned patterns, as a fixed patterns, so fixed forever, so not changed. Or these patterns might be some parameters which are learned. And now we learn to do queries on these fixed patterns and use the result of the queries in the next layer to do new queries. And here we can realize something like support vector machines, where support vectors would be stored here. K nearest neighbor, we look for the closest pattern, or a learning vector quantization. All this stuff can now be realized. I go very fast through these layers. First, layer Hopfield sets more or less self-attention mechanisms. That's a transformer attention mechanism. Here we can associate two sets. It's the R, the query set, and the stored pattern sets. And of course, we can always map into the space where the Hopfield network lives. We can both map the queries and the patterns into some space, which is done in the transformer architecture. Of course, we can do then a transformer attention, we can do sequence-to-sequence learning, we can do point set operation, and all kind of retrieval-based methods. And here we really can implement the attention layer of transformers. But we can do more. The second layer was Hopfield pooling. Here we say we store some patterns Y, and then the queries are fixed either, or can be learned, parameters are fixed. And what we can do here is we can do pooling operations, pooling over across Ys. We can do memories. We can do different things. Here, pooling or memories like LSTMs can be implemented if the Y is something like a time series. If we store a time series, important, the queries have to be fixed. We always look for the same thing, or they are learned, but they don't depend on the input. But even what we can learn is if the stored patterns have a 2D position encoding, we even can implement convolutions as known from convolutional neural networks. Also, this can be realized here. If these patterns are tagged with their position in the input. And all this processing is permutation equivalent. And the third layer is where the queries come in, but the patterns are fixed, where we can do different things. Here I mentioned a couple of them. K nearest neighbor, because we look for the most similar pattern which is stored. A support vector machine. If there are support vectors, we compare a new pattern coming in here with the stored patterns. We can do similarity-based things. We can do learning vector quantization. We can do many things where we can store either the data set here or learn representations of the data set, change even the data set, that the system gets better. These Hopfield networks have, layers have new functionalities. I skip this. This is a flow chart, how it's implemented. In PyTorch, I also will skip this. I want to go to the experiments. I want to show you a couple of experiments we did to demonstrate that this architecture is really cool, works well, and is really fascinating. First, I go to natural language processing because I know this update rules, this layer is the same as transformer. And therefore, we analyzed the transformers, especially the BERT models, in terms of the metastable state, because the Hopfield idea gave us the idea of metastable states. And we did this, and we analyzed the metastable the tension heads by seeing how many softmax components are large. What we did, we added the largest components of the softmax and counted how many components do we require to go over 0.9. If there's one pattern retrieved, only with one pattern we go over 1.9. If there are two patterns only retrieved, then the softmax has two high values. Adding these two high values with 2, I go over 0.9. And here we see a distribution for the different heads. That's a BERT model, one of these very prominent language models. That's the first layer, the second layer, from bottom to top. These are different layers. That's the last layer here. And what we see here is a distribution of these K values. This means how many patterns are retrieved, how large are the metastable states, over how many patterns is averaged. This is what you see here. And the number you see here is the mode, is something like the average number. And what we see now here is the first layer in the transformer has very, very large metastable states, is doing more global averaging, is averaging over the whole input sequence. And then from the second to the fifth layer, what's happening here, this is a large metastable state. It's not globally averaging, but it's averaging often over the half or 1/3 of the patterns. It's big averaging. And then there are attention heads of the transformer architectures, which focus on, they retrieve only 3 patterns, 4 patterns, 6 patterns. So very focused. These are small metastable states which are used in transformer architectures. And at the top, there is a medium-sized metastable state. You see it's more the greenish thing, where it's averaged over 50 patterns, 40 patterns, 20 patterns. That's this range. That's how we analyzed transformer architectures. What we know is the first layer have to provide the whole input sequence. Therefore, this averaging is necessary, that you throw in the whole input sequence into the network. And then also averaging comes. Most importantly is these layers with this small retrieve patterns. There, most of the processing is going on here. Here it's more shifting stuff around. Here the intelligence is, and here is only what we believe accessing the result, putting the result on the right place and accessing the result. But the interesting stuff is here. We used our new Hopfield networks for multiple instance learning. It's not what transformer are doing, where the memory of the new modern Hopfield networks can store all the instances. You know, multiple instance learning means there's one object. This object is described by many instances. Like you have a building, and the building is described by many photos, or many pictures of the building from different angles. You have one building, and the building is described by also pictures of the building. We used here Hopfield pooling. The data sets were immune repertoire classification and other multiple instance learning benchmark data sets. Immune repertoire classifications is we extracted antibodies from humans and did sequencing. Not we did, we get the data, and the antibodies were sequenced. And therefore, we want to know against which diseases this person is immune. Because if you have the right sequence, the right patterns, then you're immune. Problem is, you get many antibodies, and most of them are not indicative whether you're immune against a specific disease. Like for COVID, we want to know which persons are immune against COVID, which one are not. You extract all antibodies, and if the right antibodies are there, then you know this person is immune. Now, this is the immune state is what we want to predict, but the person is described by all the antibodies which were extracted and sequenced. And this is a huge multiple instance learning data set, because per person we got about 300,000 instances, 300,000 sequences of the antibodies, and we have to classify, is this guy now immune against a specific disease or not? And this is one of the largest multiple instance learning tasks ever conducted. And most methods fail because with so many instances you cannot handle this. There are very well-known multiple instance learning methods and classification methods. We compared to them, and our Hopfield networks, especially in the real-world data, which we did with some guys from University of Oslo, which did this immune sequencing, it get the best results, better than support vector machines, k-nearest neighbors, and all kind of other things. All these other data sets are simulated data sets where some diseases or some immune signals were embedded in antibodies. But important is the real world. In the real world, we outperform all other methods on the market with this new Hopfield network, because all the sequences were stored in the associative memory, and the query looked, is this specific sequence here, yes or no? If it's here, yes, this guy is immune. That was the idea, and this worked perfectly. We used also other multiple instance learning data sets. Here, there are standard data sets. It's image data sets, elephant, fox, tiger, whether these animals are on the image or not, or you see breast cancer, whether we have to classify whether it's cancerous or normal, whether it's disease or not. And here, these are images. The idea is, instead of processing the whole images, you process only the patches or the segments. And you put each segment is an instance, is a instant, and one picture consists of all the patches you extract from the image. And then we can do image classification based on this. So it's a standard multiple instance learning data set. And again, Hopfield networks perform very, very well. Out of 4 data sets, in 3 data sets, we got new state of the art. Immediately, without many fine tuning, we immediately get this, where you learn a query and you have many patches, and the query looks in the patches as some specific patterns. Perhaps for tiger, perhaps you look for stripes or for the color, I don't know. And you know which kind of picture this might be. So next data set, we tried our Hopfield networks, our deep learning architectures equipped with Hopfield networks on the UCI benchmark collections, but we selected only the small data sets. The small data sets are the data sets which have less than 1,000 examples. And this is where we say, hey, deep learning does not work for small data sets. We need a lot of data. We know deep learning architectures are data hungry. But the Hopfield networks allow something. The Hopfield network, we can store the whole data set in the associative memory, and across the layers, we always can probe the training set. Is this in the training set? Has the training set, is it the new data close to this particular sample, or is it close to this particular sample, and stuff like this? Because we have this associative memory, we can keep the whole training set in our memory and probe it again and again. And that's a big advantage, and therefore we can handle small data sets. We compared it to many other methods, support vector machine, random forest, stacking, different deep learning methods with layer norm, here neural networks, batch norm, weight norm, all kind of things. And the outcome was the Hopfield network was the best method on this small data set. That's surprising, because deep learning was not known to perform well on small data sets. But because these associative memories can keep the whole training data sets, now we get a good performance. We always probe the training data set with a new example. Is this in the data? Is that in the data? And this really gives this good performance on small data sets. That's my last data set, struct design. We applied the Hopfield network to 4 standard data sets in drug design, like for new antiviral. This data set was HIV. We should do it for COVID. Protein inhibitors. Here's a human beta secretase. Metabolic effects like a blood-brain barrier, or just side effects of some drugs, or drug candidates. We used the layer Hopfield layer and compared it to methods like support vector machine, XGBoost, random forest, and of course deep neural networks. And we also compared it to graph neural networks, where we have 4 different kind of graph neural networks. I show you the results. In 2 out of 4 of these data sets, we got with these Hopfield networks new state of the art. We got new records, and on the others, it's not performing bad. It's in the midfield, but in 2 data sets, we got a new state of the art. Also here it shows how good this new idea of using associative memories together with your deep neural network. Now, I'm concluding. The idea was to equip deep learning with associative memories. That's the idea. That's also what we humans are doing. until now it was only function approximation, but we don't, as humans, we don't do function approximation. We always have a context. We always compare to our experience. And what you can do here, you can store outliers, very extreme data points you already encountered. You can do all this. You can set your processing in context, in what you already have stored, what you already have experienced. And this is, I think, the next step we should go, not only do function approximation. Perhaps we don't have to learn all patterns. The patterns we cannot learn, we just store it. Only the patterns where we find out the rule through the neural network should be coded in the neural network. Patterns we cannot explain right now, why not memorize them? And this allows for many different mechanisms like pooling, memories, support vector machines, where the support vectors would be stored. All this kind of stuff can be implemented. This is an overview of different architectures. Now it opens up new architectures because I can design what want I to store. How do I compute my queries? Do I learn the queries directly, or the queries generated by different layers? Also, do I store intermediate results? Do I store something I computed already in previous layers? All this kind of things are possible. And this opens a complete new field. You can have new ideas how to use them, depending on what you want to store and how you want to generate your queries. Here, we also have a blog. We have a GitHub software. We have also a paper on archive, and there's also a video from Yannick Kilcher on this topic if you want to know more. And with this, I want to end and want to say thank you for listening, and thank you for also using these new Hopfield networks. You will be very excited if you use them. Thank you.
Thank you very much, Sepp. It was a lot of material, so let's see what are the questions, and let's go one by one. So the first question is, do you consider that the use of attention can eventually replace the use of convolutions in vision tasks where it is required to obtain high-level results?
Actually, yes. One of my students, Thomas Untertiner, came out with a paper. It's 16 by 16 words kind of things, where they showed they can have very good performance with attention networks. And now it's not finished. A couple of days ago, we also tried it with our Hopfield networks, and in a task where in bioinformatics, in high contents imaging, where the first 20 best performing methods were convolutional neural networks. Now we probably have a new record, but not with convolution on this image task, but with Hopfield networks, which is also can view as a attention mechanism. Yes, it will take over. Depending what you do. I know it from Tom, they used a lot of computation, pre-training. You have to invest a lot of compute and data to do this. But for our images, it's about cells, where you put the drug on the cells. It was easier because it's translation invariant and stuff like this. Yes, we will also soon show results where we kill all convolutional neural networks on this specific task. Where nobody thought image can be outperformed by other methods than image task by other things than convolutional neural networks. Now this changed.
Okay, that's very interesting. Is this information in the papers that you showed, or is this?
No, that's very new, and I don't want to reveal it. Okay. Because it's we want to build on the other result, because perhaps we can also help to make a paradigm shift. Not only convolution is used for images, but also architectures can work very well.
Okay, very good. So there is another question. Let me see. It's here in the computer. So there is one question. So could these ideas for new Hopfield networks be used to improve the capacity for storing in hardware?
Oh, that's a hard one for me because I'm not an expert in hardware. What I know, as I said, we were in contact with John Hopfield and also with Krotov, and they are more these biologically inspired guys. And they said it makes more sense biologically what they're doing. And often if it makes more sense biologically, it's easier to code in hardware. But I'm not an expert. I think it's good because you do all these updates of the associative memories locally. But I guess so, because some say it's biologically more plausible, but I don't know.
Okay, another question. So there are similarity-based classifiers and there are boundary decision-based classifiers. In your experience, what is best and for what?
We just tried it out. What we saw, it was very, very interesting. So there were some data sets, I didn't present them, where k-nearest neighbor was always the best. And now we use this Hopfield layers, and it's doing a sort of k-nearest neighbor if you do this dot products. But the Hopfield networks can do different things. For k-nearest neighbor, you have always the same k. You always took the 5 nearest neighbors, or the 1 nearest neighbor. But the Hopfield networks can one time use the closest, the 1 nearest neighbor, and another kind 5 nearest neighbor, depending on the metastable states. Sometimes the average over 5, sometimes over 10, sometimes only over 1. And this gave improvements. Nearest neighbor, always you have to choose this k. Hopfield networks can do the same and figure out what is the best k. Use it adaptively. And therefore, you don't know what the system is learning. You know it can do k-nearest neighbor, but it never is implementing one of these methods poorly. It's always some average over everything, and I don't know, not always understand what's really going on. We say it's very similar to nearest neighbor, but now here it's deviating, it's a little bit different, and it's always better.
Okay, very good. Another question. So I have one question. So you showed a lot of applications for these new kinds of networks. Do you think that generic deep learning applications can profit from this new architecture, or there are specific kinds of applications which are more suited for these new networks?
I would say you should use it always. As I should took over, you should always use them because transformers are successful. That's one kind how you use them, but you always should do that. I also got an email from Geoff Hinton. He said, yes, he always thought it's a good idea because he has also some papers in this direction. He was very enthusiastic about it. You should construct it like if the associative memory is helping, use it. If it's not helping, then ignore it. I would equip all my architectures now with this because perhaps it's helping, who knows?
Okay. So another question. So you said that you can, for example, store a support vector machine in the Hopfield network, but the support vector machine has to be trained apart using other methods, or can be trained on site, I mean on the network itself?
No, but we can do both or all, but I don't train it in the neural network because here I use gradient descent, I use backpropagation. But what I can do, I can train a support vector machine and fill the memory with the result of the support vector machine. I can also do clustering and fill the memory with the cluster centers as a reference point, so to say. I can do all this pre-processing, how to fill my memory. We didn't try everything because we don't have time and my group is not so large. But also the system itself, the neural network, can learn what it wants to store. Whether it wants to have something which we call support vectors, or something which we would call prototypes. It also can choose its own thing to store. I don't know what's better. I didn't. It's not so old. We didn't try out everything, but it's up to you guys. Try it out. Perhaps you become very famous, get a lot of money because you have a new idea.
Okay, that sounds very good. So there is a question here. I don't understand completely, but the question is, for what are useful the limit cycles in the learning of dynamic models like LSTM or Hopfield networks?
Limit cycles, I'm not sure what...
Yeah, I also was not sure about the question, but maybe it's talking about if you're learning dynamic models.
Perhaps these are the cycles where I do the cycles until it's converging. We never let the Hopfield network, we tried it once, the Hopfield network to converge to the fixed point. We only did one update and then used this update. We also tried to do more updates, that a pattern goes closer to the fixed point, but it didn't improve. Perhaps that's meant to be more Hopfield updates to go closer to the minimum. We tried it. It only cost more computational power, but it didn't help. We were very sorry because we thought it's a cool thing, but it didn't help.
Okay, so another question. So you showed that you have a special function for the Hopfield network, this LSE function. Mm-hmm. So how did you come to that function? What's the motivation behind the function?
If it's given, it looks nice, but it was more or less reverse engineering. It was what you have to know. There are two things. The derivative of the LSE is the softmax, and that would be the first idea. The softmax was in the attention mechanism, and we wanted to deal with it. And the first idea, what I saw, I gave a lecture on transformers, and then they said, yes, there's a word, and it has an attention to itself, and it has a high value. I said, what? I know this, that's associative memory. Where you have a pattern, if it's very similar, it gets the highest value. Hey, is attention the same as associative memory? Now what I had is this idea, I think attention is somehow something like associative memory, and I had the softmax. So those were the two ingredients. And then I thought, what's going on in associative memory? Then I stumbled over a Krotov and Hopfield paper, and I was a dirimizil. Dirimizil was looked very like log sum exponential. And if you now do a derivative of the dirimizil function somehow, the log was missing. There you do the normalization. Then you already are at the softmax. And with this idea, it is associative memory, having the softmax and the new energy function, you play a little bit around and say, hey, taking the log of this guy, we get the softmax, and now we have a continuous thing. That was more or less the way, putting some pieces together.
Okay, very interesting. So we don't have any more questions. So I only want to thank you for being with us today. Sure, we all know that it has been a difficult year, but now researchers are working at home, and it has become, curiously, it has become easier to connect to important speakers, to distinguished speakers like you by video conferencing. So thank you very much for being with us today. You're kindly invited to come to Mexico anytime when we have the vaccines. And I'm sure you will like to be in Mexico and give some of your talks with the new work that you are doing, which seems quite revolutionary. Thank you very much.
Perhaps I come to Mexico, but I enjoyed to be with you guys. It was fun. Thank you for the invitation. And perhaps next time in Mexico, I'm looking forward to this one.
Okay, thank you very much.
See you. Bye-bye. Bye-bye.